Hi, and welcome to a special edition of Radical Talks. I'm Molly Welch, and I'm a partner here at Radical. Today, we're featuring something very cool. It's a conversation between two of the most influential figures in artificial intelligence, Geoff Dean, Google's chief scientist and co-lead of Gemini, and Geoffrey Hinton, Nobel laureate known as the godfather of AI. Together, their work has shaped the AI era that we live in today. This discussion was moderated by Radical Managing Partner Jordan Jacobs, and it offers an extraordinary window into one of the most important and productive collaborations of the AI age. Geoff and Geoff's story is really the story of modern AI, how new algorithms would meet the infrastructure that made them work and ultimately scale. In this discussion, Geoff and Geoff reflect on everything from the early breakthroughs of deep learning to the challenges and opportunities shaping the field today. And they share a few terrific anecdotes, from the humble hardware that ran AlexNet to the early days of the Google Brain team. The conversation was recorded in front of a live audience at the NeurIPS conference in San Diego earlier this month, one of the biggest convening moments of the year for AI researchers from around the world. I'm very excited to give you a front row seat to what was an incredibly memorable conversation. I hope you enjoy it.
I'm Jordan Jacobs. I'm co-founder and managing partner of Radical Ventures. We are an AI-focused VC fund, although I spent more of my life as an AI founder, starting a deep learning company in 2010 when our joke was we had to explain to people how to spell AI when we were trying to sell to them. But had the great fortune of being in proximity to Geoff and getting to know him and working with him on the creation of the Vector Institute and some other things. So this opportunity, I think, was facilitated by Geoff Dean and Geoff Hinton being in the same place at the same time, which is fantastic. Thank you to NeurIPS. So to begin, Geoffrey Hinton, for those of you who don't know, is a Nobel Prize winner and Turing Award winner and winner of many, many other awards. Is widely called the godfather of AI. I've never asked you if you like that name.
I should not like it, but I love it.
Okay. Okay, that's good to know. I will now just call you Godfather when I see you.
Sure.
Geoff is, I was lucky to be a co-founder of the Vector Institute with Geoff. And the one thing that people do not know is Geoff makes the best carrot soup I've ever had in my life. So there's a whole other career available to him later. Geoff Dean is the chief scientist at Google and a legendary engineer who's responsible for many, many, many things that are that have kind of led to the breakthroughs that we have today in AI, including currently the co-lead of the Gemini team, which for those of not familiar and not paying attention, which I'm sure is no one in this room, has leapt kind of the leaderboard and is now the most performant model out there and has caused a code red to another company, which is interesting. So I'm really honored to have you both here together. And so to start off, there are some kind of long-standing similarities in your histories. Backprop was 1986.
No, it was 1982. But we didn't realize how good it was until 1985.
Okay. All right. I was off by a few years. I was watching cartoons then.
We didn't publish it until 1986.
Okay, there we go. And interestingly, and just I guess coincidentally, or maybe not, what brought you to your undergrad thesis? Maybe you could just describe it for a second in 1990.
Sure, yeah. So I took a two-quarter sequence on parallel algorithms, and one of the things we studied for like maybe a week in one of the quarters was neural networks. And so I was intrigued by them, and I decided it would be interesting to work with the professor Vipin Kumar at University of Minnesota. I said, can I do an honors thesis with you? And I'd like to do parallel algorithms for training neural networks. So I did. We had a 32 processor hypercube machine in the department. And I felt like, oh, if we could just get 32 times as much compute, we could make these amazing neural networks.
You must have been the first person to realize that scaling up the compute was the thing.
I mean, I didn't really even realize it myself. I did some nice, not particularly great speed up curves because I made a huge mistake. I didn't increase the size of the model as I was trying to increase the number of processors. I just saw how pathetic it became once you took your 10 neuron layers and tried to spread them across 32 processors. But it was kind of fun. I sort of created two variants. One was essentially what we now call data parallel, and one was called what you now call model parallel training. But I called them something weird like pattern partitioning and like model pipelining or something. So,
Geoff Hinton, when did you realize that more compute mattered?
So I should have realized in the late 80s when two different groups, Herb Borlard and Nelson Morgan at ICSI in Berkeley, and Tony Robinson in Cambridge, put huge amounts of effort into using parallel computation to make better acoustic models for speech. And they both got acoustic models that were about as good as the state of the art, but were better than what you got if you just used a normal processor for doing neural nets. And we should have realized at that point that if you just made them bigger, they work better. But the just making them bigger went along with very complicated programming and very complicated hardware. And so we didn't really get the lesson, and it's stupid not to, but we didn't.
When did you get the lesson?
I didn't really fully get the lesson until I went to a talk by Ilya in about 2014, but very late on.
So look, we're going to skip forward a little bit.
I didn't realize it would just keep scaling.
Right. Okay, so we're going to kind of hit some of the high points that have led to modern AI. But one of the things that I think is interesting about both of you is you've picked extraordinary people to work with you. And Geoff, you've said before publicly that the way that you are recognized is through the performance of your grad students.
Yep.
Can you share a little bit of this is a little bit off the topic, but I'll come back to it. Share some of the things that you identify in people when you're going and picking an undergrad student to join you in your lab.
So I'm really interested in people who've done something original, had an idea of their own. So one of the questions I sometimes ask people was, what's the best idea you've had? And you get people who've got straight A's in their courses and explain they haven't had an idea yet because they haven't gone to graduate school yet. They're very keen to have an idea, and you don't pick them.
Okay, so we're going to fast forward a little bit. Some of the students that you pick, both grad students and postdocs, Jan LeCun. There's a long list. We had Max Welling at dinner last night, and Alex Graves, and lots of others. And then you have Ilya and Alex in the lab in University of Toronto, which for those of you who have not been to this building, you wouldn't notice it. It doesn't look like the place that the world changed.
Yeah, we had a very small lab with no windows. That was probably good. They couldn't look out, right?
And you start working with them and ultimately create AlexNet and train it on the data set that Fei-Fei Li had created out of Stanford, ImageNet, and enter that competition. Can you just kind of talk us through why did you decide to do that? Coming back to the compute, how much compute was used for it?
Okay, so what really happened was this. A couple of years earlier, Vlad Ni had used NVIDIA GPUs for trying to recognize roads in aerial images. And it's quite difficult in city roads because you get trees, you get cars, you get shadows. And he did a very good job of that. We did that on a strategic grant from the government, which was designed to encourage research that might have industrial impact. And I applied for renewal of the grant after Vlad had showed that multi-layer nets work much better than single-layer nets, which was the crucial issue then. Do you really win by having lots of layers? And he showed, yeah, every time you add a layer, it gets better.
that's very deep.
Sorry?
That's very deep.
Very deep, yes, it is very deep. And I applied for renewal of our strategic grant. And one of the referees said this grant shouldn't be used because there was no possibility of this ever having industrial impact.
Do you know who actually said it?
I wish I knew, and I didn't keep the report because I'd like to explain to him it was 80% of the growth in the American stock market in last year. So he did this very nice work, and we then knew GPUs are really good, and we knew that from speech already. And then one day I got Alex Krzyzewski recognizing tiny images, that were about the size of MNIST, because I like MNIST. And so if you're going to do real vision, you make it the size of MNIST, and then you do real vision. And it was, I still remember Alex first trying that on tiny images and telling me it didn't work. And I went and looked at what he was doing, and he had a weight decay parameter. And I said, why is the weight decay parameter set at 1? Why, it should be set at 0.0001. And he said, oh, well, I don't know, it just seemed a good value. And what you notice about students is when they don't know anything about doing something, they appear stupid, but they're not. They just don't know. And Alex got much, much better very fast. And then Ilya said, why don't we apply this to ImageNet? It's bound to work for ImageNet. We've got to apply it to ImageNet before Jan does. And meanwhile, Jan had been trying to get postdocs and students in his lab to apply convolutional neural nets to ImageNet, and they all had something better to do. So luckily, Ilya pushed very hard, and eventually Ilya said, look, I'll pre-process the data so it's really easy. So he changed all the images so they were 256 by 256, or maybe 224 by 224. I can't. No, we should get 224 by 224 patches out of them. And it worked really well. And then I made the best management decision I've ever made, which was Alex had to do what's called a depth oral, which is you review the literature and write a review of the literature that shows you're able to understand the literature so you're ready to do research. And Alex didn't want to do that. So I said, every week your performance on ImageNet improves by 1%, you can put off doing your depth oral. And it turned out it just weeks and weeks and weeks went by.
And the compute that you trained on for this was where?
Okay, it was 2 GPU boards in Alex's bedroom, which was in his parents' house. So the good news was we paid for the GPU boards, but his parents paid for the electricity. I was, of course, doing that to save U of T money.
Naturally. And at a similar time, disbelief happens. Could you maybe talk us through the origins of it, the thinking behind it, the name of it?
Sure. So, I mean, I guess the origin of the research group, the brain team at Google, was I bumped into Andrew Ng, who had just started to spend a day a week at Google. He's Stanford faculty, and I knew him from visiting Stanford once or twice. And I said, oh, what are you doing here? Because I bumped into him in the micro kitchen. And he said, oh, I don't quite know yet because I just started a little while ago. But at Stanford, my students are starting to get good results with neural networks. So I hadn't been paying much attention to neural networks since my undergrad thesis, except I'd filed away that they were a useful abstraction and felt like kind of the right thing. And I said, oh, that's interesting. Why don't we train really, really big neural networks here? We have a lot of computers. And so what we actually had was not GPUs in our data centers at that time. We had lots and lots of CPUs, CPU machines with 16 or 24 cores each. And so I started building this software abstraction library where you could sort of specify neural networks, and it would enable you to slice up the computation with both model parallelism and also data parallelism across lots and lots of machines. And so we ended up scaling that system so that we could train a neural network that was 50 times bigger than anyone had previously trained. And we did this in the one of the most reported things that we did was this unsupervised learning on 10 million random YouTube frames with an unsupervised objective to sort of just build a good representation that could reconstruct the pixels of each frame. And we made a big mistake in that because we wanted to use local connectivity patterns for the vision. But we didn't use convolution because we wanted it to be biologically plausible, and it didn't seem like the brain could share weights across different parts of your visual system. So we ended up with these locally connected patches, but all independent parameters. So it had 2 billion parameters, but we ended up training it on the more thinly traded ImageNet 22K category thing, and got about a 70% relative error improvement relative to the state of the art, and ended up using 16,000 cores to do this training. And we definitely were starting to observe that the bigger we made the models, the better they got. And we were also starting to use the software abstraction library for a bunch of other kinds of domains like speech recognition, a bunch of other computer vision tasks. And that seemed like we didn't sort of formalize it as scaling laws, but we sort of knew we had this great saying, which is maybe like a scaling law, which is like bigger model, more data, more compute.
So you're probably the one organization at that point when AlexNet happens that is not surprised that, if you're throwing a huge amount of data at something, they haven't even done that with compute. They're running it in Alex's bedroom. But that much more data and potentially adding compute to it actually changes the game completely if you add it to a great algorithm.
Yeah, I mean, because we'd already, probably even before Alex had the results on ImageNet, we'd seen the 70% relative improvement in error rate on the ImageNet 22K thing the year before.
Okay.
Or the year of, I guess.
Yeah. And it's that summer, the summer of 2012, that you first met. Is it? Can you? I would love to hear your separate impressions of that initial meeting.
So Andrew Ng wanted to devote himself to Coursera because he thought that was the future. I think he made a slight mistake there, but and he wanted someone to replace him as someone who sort of advised the brain team who knew about neural nets. And so he suggested me. And so I agreed to go there for a summer. And I was meant to be a visiting scientist, but you had to go for 6 months to be a visiting scientist. So the only way they could actually pay me was they had to have a category, right? Because you have to have a badge and it has to have a category. And so I was an intern.
You were my intern.
Yes, I was a 64-year-old intern.
You had a green badge and everything.
Yeah, I think the only reason you could be an intern at 64 was because they only allocated 6 bits for the age. That's a nerdy.
You're only a bit older than your average intern.
And I turned up there, and I had to go to this class with the interns. So there was this big room full of students from IITs and students from Tsinghua, and just huge numbers of very smart students. And
were they wearing little beanies?
We had all had little beanies. I meant to bring my beanie hat. I still got my beanie hat. And they had this class where there's an instructor at the front and you got your laptop, and the instructor said, use your LDAP and your OTP to log on. And I put up what's an LDAP? What's an OTP? And they had 4 TAs going around to help people. And after about 10 minutes, they decided one of the TAs would be devoted to me. And all these other students were all looking around at this guy who clearly didn't know anything and was 3 times their age, really 3 times their age. And not just twice their age, 3 times. And it was slightly embarrassing. And then at lunchtime, we went for lunch. Unfortunately, one of my former students was there, an undergraduate student to take my course. And she saw me in the line for lunch. She said, Professor Hinton. And then they all looked around, oh, that's who it is. So that was kind of weird.
Okay, so that's day one. When did you first meet?
We met...
the end of day 1 or beginning of day 2 or something?
I think it was before day 1.
Okay.
I think it was on a Sunday or something like that.
Okay.
We met in a restaurant, a very nice restaurant in Palo Alto.
Tamarine. Yes.
Tamarine, yes.
Good Vietnamese food.
And we got along very well. We've always got along very well until now. And and later on, after AlexNet came out, there were all these companies wanted to buy us. And we decided we'd get more money if we pretended to be a company. Because we noticed that there's money for paying wages and there's money for doing acquisitions. And one's 10 times bigger than the other. So we decided we're going to be an acquisition. And in the end, we had an auction. But I'd sort of decided ahead of time that Google had to win because it was such fun working there in the summer. And working in the brain team was just always great.
Did you have a plan to game the entire auction then?
So what we did at the end of the auction, when the 2 people left and it looked like the wrong people might win, we just stopped the auction.
Thank you.
So, okay, and that auction took place where?
It took place at NeurIPS when it was in a casino.
Yes, at the South Lake Tahoe Casino.
Yes. And on the ground floor, there were people pulling slot machines and playing blackjack and things. And every time they won like $10,000, bells would ring. And upstairs, we were doing this auction and you had to raise by $1 million.
Yeah, that was a very weird NeurIPS because like no one who knows anything about probability and statistics wants to be in a casino and will gamble. And the casino hated us because like we didn't gamble at all.
And Terry Stanowski organized it, and he gave me a special card so I could get into the VIP lounges. And you only get those special cards if you're what's called a whale, someone who gambles huge amounts and loses. And so I would go into these special restaurants and I'd hand them the card and say, I don't gamble. And they'd look at me, yeah, right.
Okay, so you win the auction. Ilya and Alex and you actually incorporated a company. You sold the company DNN Research to Google. Maybe gamed the auction on the way to get there. Why did you want to go to Google?
Just the atmosphere in the brain team was great. The alternative was Baidu. I figured I'd never know what the Chinese were thinking. At that time, I couldn't travel, so I would never have got to Beijing. And I just knew we'd have fun at Google.
Yeah, it was really fun.
Yeah.
I feel like that was really great. That
Everybody who was in the brain team in the early days, I think, looks back on the brain team as, oh, that was such fun. It was all new. We didn't know where it was going, but everything was
bigger model, more
bigger
data.
models. They always work better. And I remember early on, having come from a university, I remember an event quite early on where we ran out of compute. And I remember Geoff getting on the phone. I could just hear his end of the conversation and him saying, yeah, 2 million would do. And I thought, I'm at a university. If you want to get 2 million more for compute, that's several years of writing grants.
And so how big was the brain team at that point?
It was about 20 people.
Yeah, we all fit in one big office, smaller than this room.
Okay, so good representation from Toronto on the team.
Yeah.
We all had desks in there, and it was good.
And it kept growing, but.
So to take us through, I mean, we'll get to Transformers in a minute, but take us through some of the things that came out of that team over the next few years.
So I worked on something called capsules, and capsules is a great illustration of what happens if you've got enormous determination. Because I've got enormous determination. And if you pick the right thing, you achieve very good results. If you pick the wrong thing with enormous determination, you spend many years working on it and it gets nowhere. So that was capsules. So, and
Capsule summary.
Early on, I got advice from two people I really respect, from Geoff and from Ilya, and they both said, stop working on capsules. That just made me more determined. But I did do some useful things for Google. So distillation was something we did, I think, in 2014. It was rejected by NeurIPS. And I remember it being rejected. One of the referees said, when you distill into this kind of student model, it doesn't do any better than the teacher, so what's the point? He just completely failed to get the idea. So, yeah.
That's a pretty useful technique.
And it turns out distillation is quite useful. Just ask DeSeek.
Do you remember who wrote that rejection?
No, it was an anonymous referee.
Okay, right.
Yeah.
Anonymous. All right, that's good, because I know that you take the receipts, and sometimes we get to hear who these people are.
I don't know who wrote the report in Canada that said that work on deep neural networks would never have any industrial impact. I wish I did.
There is a Canadian thing that is, like we've talked about. It's a kind of very interesting quirk. Once upon a time, there was a company called Research in Motion that made a product called the BlackBerry. And very kind of before you came to Google, before AlexNet, you took some of the technology that was coming out of the lab to BlackBerry. Do you want to tell us that story?
Yes.
This is if there was ever a cautionary tale, this is a cautionary tale.
So George Dahl and Abdulrahman Mohammed, Abdo, did a very nice acoustic model for speech that was slightly better than the best model. It was only slightly, it wasn't like ImageNet, it wasn't way better. It was slightly better, but it was slightly better. And the next summer, Navdeep wanted to be an intern at Research in Motion. And so I got in touch with Research in Motion and said, we've got a better way of doing speech recognition and we'd like to give it to you. Can he come and work as an intern and show you how to do it? And Research in Motion said they weren't interested in speech recognition.
Well, you didn't need it, you had a keyboard.
Exactly. And so when Canadians sort of, and actually one of the owners of Research in Motion has always whined about how research done in Canada is never exploited in Canada. It was Research in Motion that decided not to exploit it in Canada.
Just an interesting bit of history.
So Navdeep then went to Google. He couldn't actually go to the States because he was applying for a green card. And so he had to work in the Google lab in Montreal. But they got him some GPUs. And he had a very good manager called Vincent Van Hoek. And Navdeep said he wanted to just change the way Google did speech recognition. And Vincent said, you know, get a reasonable project. I mean, that's ridiculous. And Navdeep just insisted. And Vincent said, okay, well, try it. And it worked.
It turns out there's some actual applications for it after all.
Right.
Okay, so we move forward in time. Let's talk about transformers. This again comes out of Google Brain. Can you talk about the team, how they were working on it? Was there, at the time that they were doing the work, was there recognition internally that this was novel and interesting and maybe a breakthrough, or was it just another bit of research that was going to produce a paper?
I mean, I think the maybe earlier piece of work that kind of sparked interest in the general idea of transformers was the sequence-to-sequence work that Ilya and Oriol and Kwok did. That sort of used LSTMs, fairly deep LSTMs and fairly large ones, and got very, very good results on language translation initially, but it had all kinds of applications for many different kinds of sort of sequence problems. And we were continuing to try to scale up LSTMs. And I think what ended up happening was someone had the realization that if you just try to pack everything into this vector that you update once per time step, you have two problems. One is you have this sequential dependency because you need to do that computation before you can go on to the next thing. And also, you're trying to pack a huge amount of sort of interesting transitions you went through into a vector. And so if you just saved all the state and just attended to it, that would be, you know, a better way of doing this. And there was already some early work from outside Google on like attention mechanisms of various kinds.
Yeah, that was used for machine translation. So for machine translation, it's sort of perfectly reasonable to keep the English sentence before you produce the French sentence.
Right.
You weren't keeping a huge context.
Right.
And I think it was Bahadano discovered that using attention, a simple form of attention there, actually was a big win.
Right.
And then they put that into
And then
the sequence-to-sequence
put it into the transformer idea, which was basically save all your states and attend to them. And that has turned out to be really nice because you can now compute all those states in parallel instead of having this sequential dependency. And then you also have this really nice property that you can look back at all the different states you went through in order to really figure out what it is you're trying to decode, or, you know, if for encoder models, like look at much more state.
So when that first came out, I didn't pay nearly enough attention to it because I've always been interested in how the brain could do it. And it's keeping copies of all the neural activity vectors, and the brain clearly isn't doing that. So I thought, well, you can't do this in a brain, so I'm not interested. Now, in fact, you can approximate it by using fast weights. You have an associative memory, and you can do various approximations to it. It's still not clear how you would do the backprop through time to learn earlier things based on later things.
But I think that the first paper, the transformer paper, showed that you could get, you know, the same quality results with like 10 to 100 times less compute, or you could get much higher quality results with the same amount of compute. And that was clearly a big deal.
Yeah.
We also actually had similar results on scaling up the idea of having sparsely activated models, where we saw that you could get 10x improvement in sort of, you know, quality, compute to a given level of quality. And so those two things are quite complementary. So now you can have like transformer-based mixture of experts models and the 10 to 100 and the 10 to 20 kind of multiply together. And so there's actually been huge amounts of algorithmic improvements in the last, decade that have all multiplied together, in addition to the, huge investments in faster individual chips, using more chips per training run and running training runs for longer. And all those things together kind of multiply together. So now you're probably doing, billions of times more compute than we were doing even 10 years ago. And that was already, millions or tens of millions of times more compute than we were doing in 1990.
Yeah, I remember, I think it was about 2012 or sometime like that. We bought a new Titan board, and the systems guy was installing it in Vlad's computer, and he was being a bit slow. And I started doing a computation about how much time he was wasting by being slow installing this board, because it could be computing. And I figured out if I'd set a neural net running in 1986 on a Lisp machine, it would take this board 1 minute to catch up.
Is that something that you realized in real time when they were like when they were before the paper was published, before the response to it, which took a little bit of time, right? But when it was inside brain and you're seeing what they're doing, was there a feeling like this is a significant breakthrough? This is actually a step function change?
Yeah, I mean, I think that paper, we had a number of different things that seemed like pretty big breakthroughs because it was sort of a relatively small number of people doing active research in that field still. And, we were able to, explore a bunch of unexplored space and identify things like distillation, things like, the transformer, sequence to sequence models, word vector based models, in relatively short order with a, modest sized team. And so this was like it seemed like one additional big breakthrough, sort of comparable to the sequence to sequence work or the, mixture of experts or other things. It didn't strike us as, much more important. And I'm actually not convinced that it's much more important. It's certainly very, very useful, but all the things we're using today seem useful because that's why we use them.
Yeah.
So, okay. Google at that point has maybe the best business model of all time, search, and this extraordinary team of people making all kinds of breakthroughs that maybe this one doesn't feel like it stands head and shoulders above so many of the other things that are going on. You have compute and you understand the value of compute. You've understood already the value of data. At what point is there a discussion internally about we should start using this in a way that might disrupt our business or not? Or is it just we are only going to put things into production that actually aid the business? Like, is there a point anywhere along the way before ChatGPT, which we'll get to?
One little piece of historical data. I think it was before ChatGPT, Microsoft released a chatbot that started spewing hate speech, and that scared everybody.
Tay, I believe.
Right. Yeah, Tay.
Yeah. So Google...
They did online training, which is probably not a good idea.
That's a very bad idea, right? Although don't tell that to Rich Sutton.
I won't reinforce it.
So I think Google was very cautious in releasing it. And people still don't understand that Google had these big chatbots that work pretty well, like Palm, before ChatGPT. The one thing they didn't have was human reinforcement learning, and they didn't realize that you don't need many examples to stop it doing most of the nasty things it does.
Yeah, I think we actually did have an internal chatbot that was quite heavily used within Google. It was developed during COVID, and so everyone was at home, working from home. And we had about 80,000 internal users at Google, which is quite a large fraction of our 100 and something thousand employees, chatting with the system. And, people found it really, really useful. But I think we had a little bit of a myopic view because it obviously had factuality issues, as neural nets of that era did and still do to some extent, and hallucination kind of issues. And if you view that as from a search lens, that's not good because one of the most upheld core tenets of our search product is you want to be as, accurate and factual as you can. But I think we sort of didn't quite understand all the other potential uses of a chat system that are not core search things. They're like, can you help me draft a letter to my vet about my sick dog? Or can you summarize this paper for me? Or all the other kinds of things you can use these.
Can you write the paper for me?
And you write the paper for me. Can you write the review for the paper for me? I'm not that anyone would do that. So I think from a pure, like, this is a search thing lens, it didn't seem like something we wanted to put out as a product. But from a, do people find it useful? Yes, we actually had 80,000 Google employees giving, incredibly positive feedback about it being useful. So we wanted to work on factuality issues and hallucination issues more before we sort of turned it into something we exposed external users to.
Okay, and then just 3 years and a week ago, ChatGPT comes out. What was the reaction inside Google?
Code red. Was it code red immediately?
No, I mean, I think I wouldn't say that. I mean, I think I wrote a one-page memo document that sort of said, hey, we're being kind of silly here because we know scale of compute and training really good models, the more compute and data you can train on, the better the models get. We've known this for a long time. And we had multiple efforts within Google. So we had our legacy DeepMind team, we had the Brain team, we had a few different efforts across Google Research looking at, not just text models, but also multimodal models of various kinds. And then legacy DeepMind had a couple of efforts, Flamingo and there's another name. But really, we were fragmenting our research ideas and effort and also fragmenting our compute. And that didn't make any sense to me. So I said, hey, we should just all work together. Let's join forces. Let's make a single team whose goal is to build the best multimodal models in the world and invest, a joint pool of compute and see what we can do. And that was the birth of the Gemini effort.
And that was how quickly after ChatGPT?
I mean, I wrote the little document, a week or two after that, because we'd also seen that we had an internal chatbot, and we could have been the ones that released something like that. So that was a little sad, but that's okay. We can.
I have a question.
Yeah.
Does Google regret publishing the Transformer paper?
No, because I think it's had really good impact in the world.
Good. Okay.
Yeah.
Since then, Google does not publish as much. Or is that not true? Is that a misunderstanding about the policies?
I mean, we definitely publish quite a lot still. I mean, if you look at the NeurIPS program, we probably have 100 or something papers here, maybe even more. I mean, I do think we're a little circumspect about things that are mostly commercially interesting for the absolute largest scale models, because that's a very competitive space. And so we end up not publishing, the exact details of some aspects of our Gemini training recipes, say. But we definitely publish quite a lot of stuff that is on the periphery or is very early stage work that, we're not sure if it's important or not. We just want to sort of get the ideas out there and get feedback from the community, and also let the community benefit from that work.
I mean, it's been a competitive advantage in attracting talent, right? That you publish, and a bunch of other labs don't necessarily, or certainly haven't had the inclination to do it.
Yeah. I mean, I think we're a big enough research organization that we actually have quite a lot of different threads of investigation that are not sort of the core Gemini model development. There, lots and lots of basic machine learning work, and, lots of other kind of non-machine learning related research work. And so we have quite a breadth of publication there.
Okay, so I'm going to fast forward to the present, literally the last couple of weeks. You put out Gemini 3. Suddenly people remember that Google's an incredible AI company. I don't think they forgot, but they really appreciate it all over again. There are things that happened along the way that were like very, very impactful, but very long-term bets like the TPU. And I was saying to you earlier, it kind of astonishes me how much appreciation has suddenly been focused on, wait a second, Google has a structural advantage over everybody else because they have their own chips. Can you just talk us through, like, when did that start? What was the impetus for it? And how much advantage do you think it is for you?
Yeah, I mean, the origins of the TPU program are basically that I sat down and we saw that we were making lots of progress on making much higher quality speech recognition models in particular, and also various kinds of computer vision tasks, but they were quite compute intensive if you tried to run them on CPUs, which was mostly what our compute platforms were. And so I said, well, if our speech recognition gets a lot better, people might want to use it. And what if people wanted to speak to their phone for 3 minutes a day, and we had 100 million such people who wanted to do that? What would that compute budget look like if we wanted to run this on CPUs? And the math was kind of scary because it looked like to roll out this one better speech recognition model, we'd have to double the number of computers Google had. And that didn't seem very tenable. And even if it was not cost prohibitive, it would be very time intensive. And we wanted to be able to we saw that larger and more powerful neural nets were going to be useful in lots of places. So that essentially back of the envelope calculation that I turned into a slide was the impetus for starting our own custom hardware, because I also had the intuition that if you just want, neural nets have these really nice properties. They're very few different kinds of operations, and they're all very tolerant of reduced precision, because reduced precision just means noise, and neural nets like noise.
Also, you don't need error correction. You don't need error correction memory, because if you get some of the bits wrong, it doesn't matter.
Yes, exactly. Yeah, it's just like dropout or adversarial memory. So I felt like if we put together a hardware effort to initially focus on inference, because that's where most of the most compute pain would be felt if we wanted to roll it out to a large number of users, that would be really good. And we'd had a few people in our Wisconsin sort of hardware team thinking about using FPGAs, but with a bit of discussion, it seemed like we should just go straight to a custom ASIC, because the FPGA tax that you pay often eats a lot of the performance gains. And so we ended up putting out TPU v1, which was for inference. It was like a single PCIe card. And our CFO at the time, Patrick Bichette, I accosted him in the hallway and convinced him that we should deploy $50 million of these in our data centers without quite knowing how we would use them. And we ended up doing that. And they ended up being used for all kinds of things, speech and vision. We ended up using them for rolling out much higher quality translation. And then the TPU hardware folks started to focus much more on training as a much bigger scale problem, where you want to have many chips working together in concert with a super high speed interconnect. It's really much more of a machine learning supercomputer kind of thing. And that's kind of what we've now done multiple generations of.
But that going back to that first decision, or when you cost Patrick and say we need $50 million, what year was that?
2013.
Okay, so way ahead of this curve.
Yeah, I mean, we saw that the compute demands for rolling these models out for inference were going to be enormous, and this was the way to do it. And it turns out, like, we did a nice, research paper at ISCA, the main computer architecture conference. It's actually now the most cited paper in ISCA history, and that the performance results in that paper showed that we were 15 to 30 times better performance, lower latency, and 30 to 80 times, I think, better performance per watt than contemporary CPUs or GPUs. Okay. Which is a huge, huge. 2 orders of magnitude is a big deal.
Yeah. So as of today, you have the most performant model. You have a huge team spread across the world, but largely focused West Coast, London, you said New York and some other places.
The Gemini team.
Yeah, the Gemini team. You've got the data that pours in from all these products that are used by a billion plus people. You've got a business model in the background that throws off 100 billion plus of free cash flow a year. How does anyone compete with Google?
Join us. No, I mean, I'm not going to pontificate on that. I do think having the full stack of the hardware in the same organization as is also trying to build sort of advances in the models is very, very useful for us, because we can essentially co-design, and hardware takes a really long time to come out. So as a hardware designer, you're trying to forecast where is this incredibly fast-moving field going in the 2 to 6 year time frame, when whatever hardware I'm thinking about today will become relevant, probably 2.5 to 6 year time frame. And that's a really hard job. And if you have machine learning researchers sitting with the hardware people, sort of identifying, some things that maybe are not mainstream yet or seem promising but are not quite, they're a little speculative, but things you could put in hardware support or better hardware for that would be interesting, that's a big sort of much clearer lens you get into the future than if you're trying to do this without, the benefit of lots of researchers sharing their hardware ideas or their ML ideas, and how could you then put them into hardware?
Also, using ML to design the hardware has helped, right?
Oh yeah, we are. One of the projects I helped instigate was using reinforcement learning to do placement and routing in chip design, and that has now been used in 3 publicly disclosed 3 generations of TPUs, and also a couple of other kinds of chips, and has gotten better and better results each generation compared to human placement with traditional CAD tools.
Is it improving the quality of the chips, or is it speeding up the actual development of the chips, or both?
Both.
Okay, so there are all these intersecting advantages being a Google. Where do you see? So we're caught up. A number of these things have happened around NeurIPS, NIPS as it was when you sold DNN. Where do you both see the field going next? Are we going to see a replacement for the transformer sometime soon? Is it a different type of architecture, or a simulation of different types of architecture? And what does it mean for, like, where are we going to be in 5 years, in 10 years, in 20 years?
Yeah, I mean, I think there's a bunch of interesting directions and trends that I'm pretty excited about. I mean, one is, we know that when you put the right information into the context of the current models, they work quite well, because they can actually attend very crisply to, actual information they've recently seen, as opposed to, trillions of tokens of stuff that has been stirred together into, hundreds of billions of weights, where everything gets a little muddled. And so I feel like looking at mechanisms for extending the ability to attend to information is going to be really useful. So how can we attend to, billions or trillions of tokens rather than a million or a few million? And that I'm pretty excited about, because I think that might really change what you can do with these models, because they can see very clearly not just, some hand assembled set of information you put in context, but a very large corpus of all the scientific papers, or, all the videos or things like that. I think that's going to require interesting innovations in the hardware space as well. Like, how do we build much more energy efficient, much higher performance per watt and per dollar inference hardware for models we care about? I think that's going to be a pretty interesting direction, one that I'm pretty excited about. And then I feel like a lot of the models we train are not doing kind of more continual learning as envisioned by the ML community for a long time. They're sort of like a static phase of training, and then the model kind of sits there and doesn't really change dramatically as it's serving users. That seems kind of wrong.
There's a good reason for that, though, which is much safer, right?
Yeah, it's true.
You can test it. If it goes off learning by itself, it's much harder to know what it's going to learn.
No, that totally is. Yeah. But I feel like also our model architecture structures are very sort of they're not freeform in the way the brain is. And I feel like having more interesting connectivity patterns between parts of the model would be good, rather than kind of even the sparse MOE models tend to be a bunch of experts all the same size that you branch out to, and then you come back together and then you branch out again. That doesn't seem very interesting.
So give us, maybe each of you give us one or two examples of how the world, just an impact on the world that you think, let's pick 20 years from now. What has happened out there in the world because of this technology in 20 years that maybe people would not expect?
Okay, I can summarize it by a possible title for a book. If anybody builds it, either we all live happily ever after or we all die. That's what the title should have been, right? Nobody, I think 20 years in the future, nobody's got a clue what the impact of this is going to be. The impact on society in particular, because it's clear that a lot of jobs are going to disappear. It's not clear that it's going to create jobs to replace that. This isn't AI's problem. This is our political system's problem. If you get a massive increase in productivity, how does that wealth get shared around? And we don't, at least in the United States, you don't at present have the ideal government for that.
Yeah, I mean, I think I actually got together with a bunch of great co-authors last year and looked at what might the impact of AI be on, a bunch of different areas, some of which it clearly could have amazing impact, like healthcare, education, being able to create new kinds of media. But it also looked at, what is the potential impact on employment, misinformation, geopolitical issues. And I think there's a whole balance of these things. I think one of the areas I'm most excited about is how could we make scientific breakthroughs happen faster by making connections between disparate fields that in any one person's head may not really necessarily realize this other thing is important in some completely different field, or automating the loop for scientific discovery for some fields where that's possible.
So let me take off on that one thing these big models have is they're compressing a huge amount of knowledge into not many connections, only 1 trillion. And we know that to compress lots of knowledge, you have to find what's common to apparently different bits of knowledge. So I believe that when you're training these big models, they're already finding commonalities between things where people haven't ever seen the commonalities. They know much more than any one person. They're probably finding commonalities between things in Greek literature and things in quantum mechanics. And no one's an expert on both of those. Well, not many people. And
they have Greek letters in common.
Yes. Okay. So I think they're actually going to be very creative. A lot of people say, they're not really creative, they just regurgitate. That's nonsense. I think they're going to be very good at seeing remote analogies because they're doing this massive compression.
Yeah, that's sort of what I was trying to get at. Yeah.
So if we take that to its kind of extension, we think healthcare will be transformed by development of drugs, elimination of diseases, treatments at an individual level, when we understand your genome. Like healthcare, is healthcare the single biggest possible transformation in society? Or is it?
I think education may be comparable. Yeah. So both of those are very elastic areas that in healthcare, if you made doctors 10 times as efficient, we just all get 10 times more healthcare. It's not that you don't only need 1/10 as many doctors, you just get more healthcare. And with education, I think if you made education much more efficient, we know a private tutor can. And it's obvious that in a few years' time, AIs are going to be comparable with private tutors. And after that, they're going to be better than private tutors because they've seen 1 million other people. We can absorb a lot more education. And so I think those areas are going to be amazing.
Yeah.
You've been listening to a special episode of Radical Talks featuring Jordan Jacobs in conversation with Geoff Dean and Geoffrey Hinton, recorded live at NeurIPS in San Diego. A huge thank you to Geoff, and Jordan for an inspiring and thoughtful discussion. If you enjoyed this episode, we've got plenty more to come. Be sure to subscribe, leave us a comment, and stay tuned for more sessions from us at Radical. Thanks for listening.